So last time we, talked about a few questions about the modeling real world problems, how to set up equations depending on the problems. And then, we end up with differential equations in each case. So we just continue with this section. And the next problem we talk about now is draining a tank. So suppose we have a cylindrical water tank. It has hole at the bottom. Okay, so this is a tank with water and there's a small hole at the bottom. So then it's leaking. And the area of the hole at the bottom is AH or A sub H. So we want to describe the, leaking process of the water in the tank. So let the water surface be h feet high at time t. So it's just going down slowly as the water, drains. So the height h from the surface of the water to the top to the bottom, is changing. It's a function of time t. We call it h of t. And you can use the law in physics to find the speed of the water leaving the tank from the bottom. That would be square root of 2g times h if you use the gravity. Here g is the gravitational acceleration, about 32 feet per second square, I guess. Yeah. Okay. Yeah, that's a good question. We don't use negative, positive. It really depends on which axis you choose to be the positive. If you choose the downward axis to be positive, then it will be positive. If you choose the upward as the positive direction, then it will be negative. So that depends. Any other questions? So G is a constant. And the volume of water leaving the tank per second will be the area of the hole at the bottom, AH, times the speed of the water. So that's how much water leaving the tank per second. Area of the hole times the speed of the water leaving the hole. Okay. So that's a rate. That's a rate of change of the volume, okay, per second. So let's say V of T denotes the volume of water in the tank at time T. So that's the water in the tank. It just, reduces as time goes on. So the rate of change of the volume, as I just said, dV over dt, is just the negative h times square root of 2gh. So that's the rate of change as we already calculated from the hole itself. We can, set up the equation for this change of the volume of the water in the tank. It comes from the leaking. And here we do use a negative to indicate the volume of the water in the tank is decreasing. All right. So suppose that the surface area of the water is AW on the top. Okay. So that V equals AW times H. So the surface area of the water in the tank times the height of the water in the tank. That gives the volume of the tank, right? And it also changes with time. So it's a function of t, as we know. Then we can rewrite the differential equation by using, only ht. Okay, so if you plug in AW times h for the V, the volume on the left-hand side on the top, then we're going to d of AW times h over dt equals negative h times square root 2gh. And then AW is the surface area of the water. We have a cylindrical tank. So the surface area AW is a constant that can be taken out from the inside on the left. And if you do that and then divide by AW on both sides, then you're just left with d of h over dt on the left and negative AH over AW times square root 2GH. So that sets up an equation, a differential equation of the height h. The rate of change of the height of the water in the tank with respect to time t. Okay. So I didn't, put the, explicitly the dependence of time of h in the equation, but we know h is a function of time t. And if you can see the left-hand side, that automatically tells you h is a time, is a function of t. So we don't have to write down that. Does it make sense? Just imagine you have a tank, you have a leak underneath with a small hole, then you can set up the equation pretty easily in this way, right? Okay, any questions about this problem? All right, so you can also read the book, if you are not quite sure, about the drawing. I didn't draw the whole picture here, but yeah.
Would the surface area of the water be the base?
Yeah, that's the base of the cylinder. It's a cylinder, so that the surface area is always the same, whether water is up or down. Yeah, that's the base. Yes. Any other questions? So those are fixed. The only thing changing is actually the height. That's it. All right. So if no question, then we go to the next page. And this time we talk about the series circuits. So how many people major in electrical engineering? All right. So you might have seen this before. A series circuit is a circuit, electric circuit with some, capacity inductor or resistor, those kind of things, connected in series. They form a loop with current flowing through, right? So the current in the loop is the same, okay? So suppose there's a series circuit with impressed voltage E of T. Okay, so that's the power. You might get AC power, so the voltage will change with time. So it has an inductor with inductance L, a resistor with a resistance R and a capacitor with capacity C. Okay. So it has three things. So let Q be the charge on the capacitor and I of T be the current in the circuit at time T. So Q is the charge on the capacitor. Okay. So the capacitor may have some charge accumulated in it. And at the same time, we have a current flowing through the circuit. So then, from physics, we know that the current is equal to the time derivative of the charge. Okay, that's actually a definition of the current itself. The rate of change of the charge with time. That's current. Okay, then we can calculate the voltage drop across each of this device. So the voltage drop across the inductor is equal to the inductance L times dr over dt from the physics law. That's also where L is the inductance, I is the current, as we know. But if you plug in dq over dt or q prime for I, and here then you actually take the second derivative of q with respect to t. So you get the voltage drop across the inductor. Inductor is L times d2q over dt2. All right. So that's the inductor, and then the voltage drop across the resistor is just the current times the resistance. Again, you plug in dq over dt for the current I, you get R times dq over dt. Lastly, the voltage drop across the capacitor is just Q over C, charge over the capacity. So then you just add all those voltage drops. So as current flow through each element, you got the drop in voltage. So if you add them up, it should be equal to the impressed voltage. Okay, that's from the power. The power provides this voltage. All right, so you add all of those three voltages, you get a E over T. So you get L times d squared Q d2q over dt2 plus R times dq over dt plus 1 of C times Q equals E of T. So remember the voltage, impressed voltage E of T is given. That's a given function of time. L, R, C, they are all constants once you have the elements in the circuit. So that's sets up equation of the charge Q on the capacitor with time. So that's a second order linear differential equation. All right. So we end up with solving the second order differential equation. Okay. Any questions? So that's circuit. So you want to know the process of the current accumulation or dissipation and whatever. We want to know this process, physics process. And that's described by this second order linear differential equation. All right. Any questions for this example? I guess you guys in EE should be familiar with this thing. I already posted the slides in Blackboard in content. So if you want to check it, you can download from there. You don't have to write down everything on the board. Can we go to the next page? All right. So the next thing is called the foreign bodies. So so we are considering an object free fall downward, okay, from the earth, from the sky or whatever. So a body with mass m is falling downward due to gravity, and the displacement of the body at time t is s. Okay, it goes down s distance at time t, after time t, from the release. Ignoring air resistance, we have the equation from the Newton's second law. The mass m times the second derivative of the displacement with time is equal to the gravity force, mg. So if you cancel the mass m on both sides, you get the d2s over dt2 equal to g. I'm sorry, it should be dt2, not d2t, okay? The second derivative of displacement with respect to time. So that's again the second order differential equation, linear for the displacement. G is a constant, as we know, just as before. So that's the case when there is no air resistance, or we just ignore it when the speed of the body is small. We can ignore air resistance. But as the body goes down more and more, if you let it go from very high, then you have to consider the air resistance. It becomes more and more important, and it's actually proportional to the speed. So the faster this body goes down, the more resisted it gets from the air, or resistance. So so let's consider falling bodies and air resistance. So if air resistance of the falling body is included, and the air resistance is proportional to the velocity of the body, okay, and opposite to the direction of the velocity, of course, then we just include the force from the air on the right side, which is negative kV, because it's always opposite to the displacement or velocity. So we got an equation of m times d2s over dt2 equals mg minus kv. Again, there's a typo here. It should be dt2, not d2t. Okay. So the difference between this case and the previous case is just that we just add the air resistance on the right side for one additional force to to the opposite direction of gravity. Yes.
Is K constant?
K, it is constant. Yes. Yeah. Constant. Yes. And then we can rewrite this equation by using the velocity v is equal to ds over dt. So the velocity is the first derivative of the displacement with respect to time. as we know that. Then we can rewrite the whole equation as m times d2s over dt2 equals mg times k times ds over dt. So again, we got the second order differential equation of the displacement s with respect to t. And it's also linear. All right. So where k is a proportional constant, that v equals ds over dt, a is the velocity of the body. Any questions about this problem? Yeah, I think this is pretty straight if you took physics before. Okay, last thing is about the suspended cables. So this time we got a different problem. We have a suspended cable or rope. You know, you just hold the rope, and you want to ask what's the shape of the rope. Okay, so a suspended cable is shown below, and consider the segment P1, P2 of the cable where P1 is the lowest point and P2 is any other point on the cable. So you just consider the lowest point P1. So you know it has to be at the lowest point in the middle. So we call this P1, and any other point that we call it P2. Then we consider this segment P1, P2 and the forces on this segment. All right, so it has two forces of tension from the rope itself on the left and the right. Okay, so we call them T1, T2. They are the tensions at P1, P2 respectively. Okay, so P2 is upward, P1 is horizontal, right? They have to be tangent to the rope itself, the tension. Okay, so let's say theta is the angle of T2 measured from the positive x-axis. So T2 is the angle of, theta is the angle of T2, basically. Okay, so that describes the direction of T2, basically theta. And let's say W is the weight of the segment, P1, P2. And then we can use the forces balance to set up the equations for this segment of rope or cable. So if we just decompose all the forces along the horizontal or the vertical axis, so how many forces do we have? We have two tensions, T1, T2, and the weight, gravity, right? So you can decompose T2 along the horizontal and the vertical axis, and then use the balance of the forces. So we got W equals T2 sine theta. That's the vertical component of T2 should be balanced by the weight. Okay, and the horizontal component of T2 is balanced by T1. So T1 equals T2 cosine theta. Okay, but at the same time, we know T2 is tangent to the cable, to the curve. That's always the case. So tangent theta equals dy over dx. So y is a function of x. Well, this is rope. Okay, so dy over dx is just the tangent theta. The slope of the tangent line is the derivative, right? So then we can rewrite this equation a little bit. If we divide the W and T1 on the left-hand side of those two equations above, then we got T2 sine theta over T2 cosine theta on the right side. T2 cancels, and sine theta over cosine theta is tangent theta. But then tangent theta is dy over dx, as we just mentioned. So the whole thing just becomes an equation with W over T1 equals dy over dx. Okay, so then we can start from there to We need to go to a little more details to solve the equation. This is still not a complete differential equation with everything identified, but this is the start to solve, to tackle this kind of problem. Any questions? Okay, so I guess I'm going to stop here. If no question, I'm going to stop the recording.